Welcome to the Explainer. When you're learning calculus, there's one idea that's absolutely fundamental to everything else, the limit. But let's be honest, the thing that trips almost everyone up is trying to prove it. So today, we're going to demystify the formal proof once and for all.
We all kind of get what it means when we say a function is getting closer and closer to some number. That part's intuitive. But in math, close just doesn't cut it. You need something solid, something you can build on. And that's exactly what we're digging into today. The formal epsilon delta definition of a limit. And trust me, it's the very bedrock of all of calculus.
All right, so first up, why do we even need this? Why isn't just saying it's getting closer good enough? Well, think of it this way. Intuition is a great starting point, but you can't build a skyscraper on a fuzzy idea. And that's really what calculus is, a giant, beautiful skyscraper of logic. To build things like derivatives and integrals, you need a foundation made of absolute rock-solid precision. The idea of getting closer is just, well, it's too mushy. We need to make it concrete. So how do we make this idea of closeness concrete? Here's a thought. Let's stop thinking about it as some dried, stuffy definition from a textbook. Instead, let's reframe the whole thing as a game, a challenge of precision. The rules are actually pretty simple. Imagine two players. Player one, the challenger, sets a target and says, I bet you can't guarantee your function's output will land this close to the limit. Player two, the prover, has to respond, oh yeah, I can, as long as I get to control my input. It's all about making a guarantee you know you can. Let's meet the player's tools. The challenger's favorite tool is a tiny Greek letter, epsilon. Think of epsilon, or as setting the size of the target zone on the y-axis. The challenger can pick any positive number, no matter how small, and say, okay, wise guy, can you force your function's output to land within this epsilon distance of the limit L? And now for the prover's move. They respond with their own Greek letter, delta, or delta. Delta is all about control. It sets up a control zone on the x-axis, around the point A. The prover says, you bet I can. As long as you pick an x value that's inside my little delta zone, I promise the output will land right inside your epsilon zone. And this is the absolute, non-negotiable rule of the game. If you pick any x value from inside that delta zone, the resulting function value, f of x, must land inside the epsilon zone. Not maybe, not sometimes, every single time. It's an ironclad contract. So let's play around. Imagine the challenger is feeling a little generous. They give you a huge epsilon, a target the size of a barn door. Well, finding a delta that works is a piece of cake, right? You've got tons of wiggle room to work with. But then the challenger gets serious. They shrink that epsilon way, way down. The target is now the size of a pinhead. So what do? Well, you have to be more careful. You have to shrink your delta zone, tightening your control over the input. The harder the challenge, the more precise your response has to be. And here it is. This is the heart of it all. This is how you win the game. A limit exists if and only if you have a winning strategy. It means that no matter how ridiculously, impossibly, microscopically tiny the challenger makes that epsilon target, you can always find a corresponding delta that guarantees you'll hit it. If you can always win, the limit exists. Okay, so now that we've played the game, let's go back and look at that scary formal definition. You'll see it's really just the official rulebook for the game we were just playing. All right, deep breath. I know, at first glance, this just looks like a jumble of symbols designed to make your brain hurt. It's intimidating, but trust me, with our game in mind, we can decode this thing piece by piece. Seriously, it's not as bad as it looks. Every single part of that definition corresponds directly to one of the rules of the game we just talked about. Let's map it out. Check this out. For every epsilon greater than 0, that's the challenger's move, right? They get to pick any target size. There exists a delta greater than 0. That's our response. We can always find a control zone, such that if the distance from x to a is less than delta, that means picking an input from our control zone. Then the distance from f of x to L is less than epsilon. And that's the payoff. The output lands in the target zone. See, it's a perfect play-by-play of our game. Okay, so theory is great, but how do we actually put this into practice? How do we write a proof and show that we can always win this game? Let's get our hands dirty with an example. So here's our mission. We need to prove that as x gets closer and closer to 1, the function 2x plus 1 gets closer and closer to 3.
Our job is to find that winning strategy, that formula for delta that will work for any epsilon the challenger throws at us. And the good news is, there's a reliable game plan for building these proofs, a kind of 5-step battle plan. First, you accept any challenge. Then, you do some detective work to find your delta. After that, you just follow the logic to show that your strategy actually works, and victory is yours. I absolutely love this quote from the OpenStax calculus textbook because it just nails it. When you see there exists, it's your clue. It's telling you to go on a scavenger hunt. And what's the treasure you're looking for? A formula for delta. That's the whole key.
So how does the scavenger hunt actually work? Well, a lot of the time, the secret is to do a little bit of scratch work off to the side. You start with what you want to be true at the end. You want the distance from your function to the limit to be less than epsilon. Then you just do some algebra. You simplify it, and look what pops out. It simplifies to either x minus 1 needing to be less than epsilon over 2. That's our treasure map.
And bam, there it is. Scavenger hunts complete. We've found our winning strategy. The scratch work told us exactly what our move should be. We just choose our delta to be exactly epsilon divided by 2. If we make that our rule, we are guaranteed to win the game every single time. It is a foolproof strategy.
Now, this is a pretty slick trick, right? But it's so much more than that. This whole framework, this epsilon delta game, is incredibly versatile. You can tweak the rules just a little bit to define all sorts of other precise concepts in calculus.
For example, what if you want to define a one-sided limit, like a limit from the right? It's so simple. You just change one tiny part of the rulebook. In the rule for our control zone, you just drop the absolute value bars. That's it. Now your control zone is only on one side of A. A tiny change to the rules gives you a whole new, perfectly precise definition.
And really, that's the big takeaway here. The epsilon delta definition isn't just some weird hurdle you have to jump over in calculus class. It's a blueprint. It teaches us how to take a simple, fuzzy, intuitive idea like getting closer and build a fortress of pure logic around it. And once you have a tool that powerful, you can build anything. You can build the entire world of calculus. Which really makes you wonder, right? What other intuitive ideas are out there, just waiting for us to make them precise?